In this video, I'm going to prove the ideal gas equation, PV equals nRT. I'm going to do this quickly because I'm lazy, but I'm going to have lots of animations that will take a long time to do, because I have standards. We're going to prove this equation the same way physicists did, by making assumptions that are at least partially incorrect every time we get backed into a corner. Watch as we slowly get further and further detached from reality for the sake of an equation that has 4 unknowns in it anyway. Was it worth it, physicists? Was it? Anyway, let's begin. This equation mostly comes out of considering what happens when particles hit the walls of whatever container they're in. Assumption number 1. Already? No energy is lost in this collision, and so the overall speed is the same before and after. Physicists will call this a perfectly elastic collision. I call it the GLaDOS principle. Speedy thing go in, speedy thing go out. In addition, the particle bounces off at the same angle that it approached. This means the change in velocity in the y direction is 0. In fact, assumption number 2. The density is constant. If any particle leaves the area we're considering, we'll just say another one comes in. This means we can basically ignore the y direction. And you can almost make this assumption true! Anyway, if the particle was approaching with speed v, speedy thing go out with speed v, and the change in velocity is minus 2v. As momentum is velocity times mass, the change in momentum of a particle is minus 2mv. Assumption 3. The laws of physics are true. This might sound flippant, but anyone studying relativity will let you know that this is quite useful to establish, mainly Newton's laws. According to the second law of motion, the force on the wall is the same as the rate of change of momentum, or, as stated in a useful way, F equals minus 2mv delta t. Minus 2mv is our change in momentum. Delta t is the time it takes for the collision to elapse, and is even smaller than the confidence people studying relativity have in the laws of physics. If that is the force for a single collision with a single particle, you can easily adapt it for multiple particles. M becomes delta m, the total mass of every particle colliding in that area. Delta t is the overall time frame that we're considering, and v becomes v bar, the average velocity in the x direction. Unfortunately, this means we have to think in 3 dimensions, although I will continue to think in 2 dimensions, as the y-axis never did anything for anyone. Let's say the collision is happening in this area. This area is not going to be neat, because later on it will make me look smart. The total mass of particles involved in this collision is half density times volume. The half is because half of the particles will go in the direction of the wall, and half will go in the other way. This assumption is almost true, because we assume movement is random, and because of the massive number of particles, it basically is, and the expected result is 1/2 of all particles move in each direction. Unless you had a fan inside your container. I'd like to see the physics teacher who set me deal with that. The volume that we're considering is given by the length times the area. The area is squiggly and ugly, but the length is the average velocity multiplied by delta time. The distance it travels per second multiplied by how many seconds you're considering. Look! Delta m. If we go back to our equation for force and politely ask delta m to move aside for its equation, we get this. Ugh. However, that simplifies to this. F equals minus density times area times velocity squared. The time taken doesn't actually matter in this equation after all. This is the force the wall exerts on the gas. However, we had the foresight of saying that the laws of physics work, which was a risky move, but does allow us to say that the force the gas exerts on the wall is density times area times velocity squared. Thanks, Newton. 3rd time's the charm. Now then, time to actually introduce a relative variable. Pressure on the wall. Pressure equals force divided by area. Here, pressure equals density times area times velocity squared divided by area. Or, pressure equals density times velocity squared, and the squiggly area doesn't actually matter. I hope that makes me look clever. I'm sure those reality-defying physicists, however many years ago, felt clever. Now then, time to actually consider more than one axis. Except no, through Pythagoras' laws, which are too cool to be labelled assumptions, we can figure out what the overall speed is. And as movement is random, and there is no preferred direction in random movement, unlike me, the Almighty doesn't have it out for the y-axis, the overall average speed squared equals 3 times the average x speed squared, which is technically what we were considering before. This lets us change our pressure equation to this. Poor y-axis. Allowed out of the cupboard under the stairs, only to be abstracted away so quickly. Sadly, velocity isn't terribly useful, as we can't spy on each and every molecule, and if we try, the laws of physics sometimes get petty. Instead, let's work with the energy of the particle. According to the formula for kinetic energy, v squared equals twice the kinetic energy divided by the mass of a particle. As a result, pressure becomes 2/3 times density divided by mass, all multiplied by the kinetic energy of a single particle. Mass and energy are almost in our target equation for reasons that will become clear later, but I'm starting to get sick of this density term. It's like it's turned up to our black tie deriving session in trainers. Let's take out the trash and bring in the big guns. Knock knock, who's at the door? That's right, it's GCSE chemistry. Density equals the total mass of the volume divided by the volume. The total mass equals the mass of each particle multiplied by the number of particles. The number of particles equals the number of moles of a particle, a unit used in chemistry with its own history, multiplied by Avogadro's number. This number is defined by the number of times you will use Avogadro's number if you pursue a career in chemistry. It also tells you how many particles are in 1 mole. Fortunately, we see a mass term on top, and in our actual equation, one on the bottom. After that has been cast into the fire and destroyed, we can substitute into the original equation. P equals 2/3 times energy times the number of moles times Avogadro's number, all divided by volume. Multiply everything by volume, and we get the PUV part of PUVnRT. The last thing we need to bring in is the equipartition of energy. This describes how the temperature of a gas, assuming the temperature is constant throughout, which it almost can be, relates to the kinetic energy of each particle. The energy per particle, 3/2 of the temperature in Kelvin, multiplied by Boltzmann's constant, about 1.38 times 10 to the minus 23 joules per Kelvin. Boltzmann, as well as being called Boltzmann, was so passionate about his frequently dismissed equations and theories that on his grave, he had his equation describing entropy engraved above a bust of his own head, with the most "I told you so, idiots" expression it's possible to implant in stone. Dying well, it's the finish line. With substitution, PV becomes 2/3 times the number of moles times Avogadro's number times 3/2 times the Boltzmann constant times the temperature. The fractions cancel. Physicists will say this is proof of the perfection of mathematics. Personally, I think the 3 divided by 2 exists solely to make this fraction cancel. You weren't fooling anyone, Boltzmann. We were only human. In addition, our 2 constants multiply to make another constant, the gas constant. This one is the in PUVnRT, and is approximately 8.31 joules per mole per Kelvin. Take note, scientists, you don't need big exponents and everything. Just a mantissa will do. Honest. Anyway, once all this is done, you get pressure times volume equals the number of moles multiplied by R, the gas constant, times the temperature in Kelvin. As I like to say, PV equals nRT, and as I like to remember, PUVnRT. This equation can be used to estimate pressure, volume, the number of moles, or temperature, as long as you know 3 of the others, and are okay with your answer being almost certainly incorrect by at least a bit. Goodbye.